For the next talk, I would like to invite Professor Michael Geller from Tel Aviv. And as you heard earlier today, Yuval initially wanted to study gravity. He ended up studying particle physics, but he was always interested in gravity. And Michael will tell us about some fascinating connections between cosmology and particle physics, which is very fitting in this context.
Yeah.
Thank you.
So thank you very much. And thank you again for inviting me and for organizing this wonderful workshop. I'd like to talk about something a bit different from the talks that were already here today. And it's going to be more, I think it's not going to be a big program, but more curious, interesting possibilities that maybe we can measure, or we can say something about particle physics from cosmology. Okay, so the first question would be, what do we know about cosmology? So we have been talking about particle physics all day, but we have a lot of data from cosmology that has been taken already for more than 100 years. And we know a few things very well. We know first that the universe expands. We have been measuring this since the 1920s. And we also know that on large scales, beyond the galaxy scale, beyond the galaxy cluster scale, the universe is extremely homogeneous. And this property persists in everything that we measure. And specifically, it is very clearly seen in the cosmic microwave background, the microwave background that comes to us from the early universe. And it is extremely homogeneous to the level of 1 in 10 to the 5. And not only that we have measured the CMB and now measured its perturbations and its spectrum, we actually reproduced it. And we completely understand not only the homogeneous part, but also the very small 10 to the minus 5 inhomogeneities that appear on top of it. And so we know the spectrum of the homogeneous part, which is a very good black body spectrum, and we know the properties of these perturbations that are just different. You can see them. They're different densities of this microwave signal in different regions in the sky. Okay, and we understand this in what is known as the standard cosmological model, or the lambda CDM, and it's basically has a homogeneous expanding background that is governed by the Friedmann equations, which are basically the equations of general relativity in this context, and with several components. So we have the standard model baked in, and we have the standard model particles, which there appear as baryon, photon fluid, electrons, and neutrinos. All of these are very important. But we also have to add two new components. One of them is the dark matter, and the other is the dark energy. And so these components drive the expansion. But also, in all of these components, we add in some initial inhomogeneity spectrum that we believe comes from inflation, but it is not important for this endeavor. And we assume about it that it is statistically uniform, and it comes with some power spectrum, i.e. some intensity of this noise, okay? And so then we fit, with this model, we fit to the data, and the fit is incredible. And I have to say, it's incredible. First of all, we completely reproduce not only the inhomogeneities in the CMB, but also the polarization of the CMB, the homogeneities and the polarization of the CMB, and the power spectrum of a large-scale structure, which is just measured by counting the number of galaxies in each angle in the sky. And importantly, the CMB would not be reproduced if we change the QED properties even a little bit. If we change the levels of the hydrogen atom a little bit, that would completely screw this very good agreement. So this agreement really bakes in everything we know about particle physics and about GR, which I think is really a great feat of science. Okay, and then we take all of this feat, and we just have basically 6 basic parameters, which can be parameterized as the following. It's basically the number of baryons, which is how much standard model stuff is there, the number of how much dark matter we have there, some properties about reionization, which is what happens when the universe becomes ionized when galaxies are formed, and the properties, well, how much dark energy and the properties of this initial power spectrum, which is these two last parameters. So these 6 parameters govern everything. We feed it, and you can see that this is now a precision science, that the fit is very, very good. And from this, we get how much, what is the composition of the universe today, how much cold dark matter is there, how much baryonic matter, and how much dark energy. And I guess this is a very well-known picture. We know by now that our stuff that we see in the lab every day is just about 5%. So I take this as a motivation to study what can we say more with the data that we have about what can possibly appear in the model of the universe. Okay, so about that, I'm going to talk soon. Okay, so with this model, we now understand the history of the universe, and we can take it, and we can also reproduce with it very well the primordial abundances of the first elements, which is mostly deuterium, helium, and lithium. And with this, we know the history of the universe very well from this point, which is this 1 second. I say no because I'm going to modify it soon, and I'm going to say what do we actually know and what we don't know. But it is very hard to modify anything in the universe after that first second. Okay. But what happens before that is still an open question. And so we can go back with several events in our universe's history. So we go from the present, we go back to a recombination where the cosmic microwave background was emitted, and the nucleosynthesis where the first elements were formed. And we go beyond all the way to neutrino decoupling. From this, this is all pretty set. It's very hard to change anything here. But if we theoretically go beyond that and assume that the universe was even smaller than what it was in the first second, then it means it was also much hotter. And at some point, it would be so hot that QCD would go through a phase transition. That's not a precise statement, but it will go from being described by baryons and mesons to being described by quarks and gluons in a plasma. Okay, and similarly, if you go even further to where we get close to the energies that are associated with the electroweak physics, then we would get that electroweak phase transition occurs, and instead of having massive gauge bosons and fundamental fermions, we would move to massless plasma of massless fundamental fermions and gauge bosons. And so these phase transitions, we don't know if they occurred actually, because we don't know if the universe was ever hotter than what it was at the first second, but it is very plausible that they did occur. Okay, and these in the standard model, these phase transitions are actually crossover transitions, and so not much interesting will happen to them because they are just smooth. We just smoothly go from one phase to the other. But especially for the electroweak phase transition, which has to do with the Higgs properties, this is not yet verified. We have not measured the Higgs self-coupling, which is what governs this property of the standard model. And in fact, it could be that at least the electroweak phase transition is a first-order phase transition. Okay, so what is a first-order phase transition? A first-order phase transition is a transition where the free energy, which is what Misha was mentioning before, does not change smoothly, but rather changes such that the global minimum of the theory as the temperature goes down is discontinuous. And so then, instead of the entire universe going smoothly from one phase to the other, what happens is that it cannot go smoothly because locally you cannot go from one phase to the other. And so what you get is you get tunneling, and essentially you produce bubbles. And these are bubbles we know from everyday life, from like vapor bubbles in water. But in the early universe, these bubbles have a very, very exciting consequence. And that consequence is that if you look at what happens to these bubbles, these are bubbles where the a big part of the energy density of the universe is now inhomogeneous. So inside the bubbles, you are in the new phase. Outside of the bubbles, you are in the old phase. And there's a big vacuum energy difference. There's a big energy difference. These bubbles are extremely energetic compared to the energies of that time. And they grow very big. And what happens is that they grow big and they collide. And once they collide, they can produce gravitational waves. Okay, and this is one of the most exciting properties, because these gravitational waves, once emitted from the early universe, from these bubble collisions, they can survive until today. Their energy density of these gravitational waves can be comparable to the energy densities in just regular radiation, regular CMB radiation. And what happens is that then these can be discovered by just the next generation of gravitational wave experiments, such as LISA, which was recently approved. And there's more similar ideas that are more futuristic for the next few decades that go even beyond LISA in sensitivity. And if you look at this plot, which for everyone who has been searching for gravitational waves is already pretty well known. So what we see is different frequencies of gravitational waves and the sensitivity plot of LISA, which is everything beyond that line can potentially be discovered. This is all very still theoretic. Hopefully it will happen and we don't get backgrounds and everything. But in this purple region is where a sort of electroweak-like phase transition can live if it is first order. And so it is possible that we could see such a gravitational wave background with LISA. Okay, so interestingly enough, and this is something that we have worked out in my postdoc together with Yushin Tsai, Anson Hook, and Raman Sundrum, which is that there's even more data in the gravitational wave signal than what was previously thought, because just as the CMB, the gravitational wave signal would not only have just a very interesting frequency spectrum, which is similar to the black body of the CMB, but also it would be inhomogeneous because the universe was inhomogeneous at that time. Okay, and so we would see hot spots and cold spots in that gravitational wave background. So we would see an anisotropic pattern. And very interestingly, the gravitational wave was emitted way, way before the CMB. If we measure it, that means it was emitted before the first second of the universe. So this is going to give us even further, earlier information about the universe and how these inhomogeneities look like in the early universe. Really, what it would measure is the innate properties of these inhomogeneities, how they were produced, which we think happened as quantum fluctuations during inflation. And this signal could give us this. But of course, if the inhomogeneity is at the same level, as the CMB one, then the signal can be quite small, but it doesn't have to be. It could be that the inhomogeneities in the sector that, so if this gravitational waves were emitted not from the standard model sector, but maybe from a dark sector, they could be actually much bigger. So let me just plot how this would happen. Okay, so this is in a very, very similar to the CMB. So if this is the surface of last scattering, the surface where the universe became stopped being opaque and the photons could travel, and this is where the CMB was emitted from. Okay, if the universe was homogeneous, we would have a uniform redshift from every point. So roughly, these inhomogeneities could be thought of as an inhomogeneity of this last scattering surface. And so they would produce inhomogeneous photons and produce cold spots and hot spots in the CMB. This is actually a pretty good, I think, explanation for the adiabatic spectrum that we see in the CMB. So if you want to ask me, you can ask me about that later. But very similarly, even if we go further in distance, so even earlier in the universe's history, we would get a similar thing for the gravitational wave background. It would also be inhomogeneous surface of the production of the gravitational waves, or the phase transition, the surface of the phase transition, and similarly, we would have an inhomogeneous signal. And this inhomogeneous signal is living somewhere here if it is the same inhomogeneities that govern the CMB signal. So they are barely visible at LISA, probably not. And so we would need, if we do measure at LISA a homogeneous spectrum, you would definitely need to build a more next generation experiments which can have also like an angular resolution to discover the signal. And in the paper, we have shown that it is actually possible, and at least theoretically, one can measure it. Okay, but then we started thinking, or I started thinking in the last 5 years, even more broadly, which is that since we are looking at a potential signal of a phase transition that in the standard model it does not appear, but it gives us a very clear observable signal, it is interesting to see what are the entire spectrum of possibilities of what could happen. Because when we started with lambda CDM, we did not expect that we would need extra components apart from the standard model components, but we saw that these extra components are there, and in fact we are still not sure whether the dark energy is actually a constant or not. This is still not measured to a precision that is good enough to tell us. And so we actually are not sure about, at the precision level, what happens in the dark sector, which governs dark matter and maybe dark energy. And so we started thinking, well, what would happen if you look more broadly at phase transitions across the board that can happen at any temperature, okay? And so interestingly, they're already with gravitational wave experiments, they probe a big part of it, so LISA is here, but there has been also this effort with pulsar timing arrays, which give us also a measurement of the gravitational wave background, which we think right now it's a standard model background. But potentially, if you improve the sensitivity and you can resolve it, you can also measure a primordial background. But if you go even below, even in temperatures lower than this, then you at some point hit the CMB region itself. And there has been works that try to constrain gravitational waves with the CMB, including those that come from phase transitions, but more broadly, those that come from inflation. But then we started thinking about what would really happen if you have phase transition at around the CMB time. So around the time that the CMB was emitted. This is about 400,000 years after the Big Bang. Okay, so interestingly, if the phase transition happens at the CMB and you produce bubbles at the CMB time, or even after the CMB and before today, what would happen is that these bubbles would produce a new inhomogeneity that would be not the primordial inhomogeneity, but a new source that would be that would change all the properties of the CMB that we know. And in fact, the CMB and the large-scale structure that I was describing in the beginning of the talk are highly sensitive to such an inhomogeneity because the universe is very homogeneous, and we have measured that it's homogeneous to the level of 10 to the minus 5. So if we assume that there is some inhomogeneity in the new inhomogeneity in the universe, it must be less than 10 to the minus 5 of the homogeneous part. So in fact, we are very, very sensitive to it. And it's not only gravitational waves, which is what is true for earlier phase transitions, but here, because we have so much data, it's everything. It's scalar perturbations, it's temperature perturbation, it's vector perturbations, it's tensor perturbations, it's really everything, okay? And so one can ask, yeah, that's very nice, but who ordered this? Why should there such a phase transition appear? But interestingly, there are very simple models, and this is something that we are inspired by the QCD, which is very much the topic of this workshop and Yuval Ne'eman's greatest achievements. And interestingly, the QCD is is such that the scale of confinement of QCD and the scale of the phase transition is an exponentially sensitive parameter, as we all know, and of course from David Gross's seminal work from asymptotic freedom. And in fact, slightly different values of the gauge coupling at the cutoff would result in exponentially different values of the scale of the phase transition or the temperature of the phase transition. And interestingly, if we have such another QCD-like theory, maybe that dark matter is charged under, or it just appears there, then if that scale is between the milli-EV scale and the EV scale, or even above the EV scale, then cosmological probes are highly sensitive to it, to the level of if 10 to the minus 5 of the energy density of the universe is in that sector where that QCD lives in, we would be sensitive to it. So we know dark matter at the level of order 1 of the energy density of the universe, but if we have something inhomogeneous, we are sensitive at the level of 10 to the minus 5, and I think that's why it's very interesting to search for it. Okay, and so what would be the phenomenological consequences of this? And so there are two main effects that we're looking at. So we have these bubbles that are produced at some point after the CMB. This is the scenario we focused on in the first work. And so there are two main effects. First of all, these bubbles, they create gravitational potentials, and dark matter falls into these gravitational potentials. And so then what happens is that they change the distribution of galaxies in the sky. Where the bubbles appear, there's a perturbation in the number densities of galaxies in the sky because there's a new source of gravitational potential. And this would change the large-scale structure observables, such as these galaxy counts. But also the CMB photons travel through this background of these bubbles, of these new gravitational potentials. And as the bubbles expand, the gravitational potentials change. And so the photons enter and get one redshift when they enter, but because of the change in the background, they get a different redshift when they exit. And that creates a new temperature anisotropy in the CMB. And so this is known as the integrated Sachs-Wolf effect or ISW effect. And this is also something that one can measure. And in the current work, because phase transitions are very complicated and bubble dynamics are extremely complicated and depend on whether there's a plasma effects or no plasma and whether there's turbulence or no turbulence. So we take the simplest approximation first, which was also done, by the way, for gravitational wave measurements. We just assume what is known as the envelope approximation, which is that the bubbles, they grow with the speed of light, and when they collapse, the bubbles just merge. Okay, so we then can use the bubble statistics to mostly analytically calculate this effect. I show you a plot of how we're doing this, but I don't have much time to go over it. But it, of course, needs to be confirmed with more realistic simulations, as has been also done for gravitational waves. Okay, and so this is the effect we see. So if this is the regular lambda CDM, if there was a phase transition with roughly here, there's, I think, about 10 to the minus 2, or I think slightly more, 10 to the minus 3, and of the energy density of the universe, you could see that we would get another peak in the CMB for low L. The reason why it's for low L is because we were taking phase transition that happened quite late. So the bubble sizes that correspond to this are roughly horizon scales at later times, which is roughly from this point on. So we expect a signal somewhere here. And we can already set bounds, and you can see that the bounds from integrated Sachs-Wolf, they slightly depend on the length of the phase transition, which is the red and the blue lines. But everything above that line is excluded, and we can see that for phase transition occurring at every redshift from 0 to 1,000 roughly, we exclude a region of about 10 to 100 times 10 to the minus 5 of the energy density of the universe. Okay, so I think that's very interesting. And so what we plan for the future is that so here we are taking bounds and projections for future experiments using just 2-point functions, which is a very good measure for for the Gaussian white noise that the CMB is, but the bubbles produce a signal that is vastly different. And so we want to try to design what is the correct signal and what is the correct measurement that we should do, or take from the CMB, for instance, use these spatial maps instead of doing this Fourier analysis, and use that to get, I think, a much better handle on the sensitivity. Okay, so let me conclude that we are currently collecting vast amount of data in cosmology, and there might be also beyond standard model physics hiding there, for instance, new phase transitions that can lead to new observations. Of course, there's no guarantee of success. Nobody told us that such a phase transition occurs. And so therefore, we should cast a very wide net with all the experiments that we have and see what they're sensitive to on, of course, reasonable models. And I think that's what we are trying to do with this program. So thank you.
Thanks very much, Michael, for this fascinating glimpse of a possible future. I think just as is true about the earlier talks, Yuval would have been delighted to hear this one. And
thank you.
We have time for one question. Please.
Hi, so one question about the first part of your talk about maybe probing an electroweak phase transition. Would it be at the level that you can say if it's good for baryogenesis or not?
So that's a complicated question. Good. So I should say that for baryogenesis, also one of the Sakharov conditions is the well-known fact that there should be an out of equilibrium dynamics, and bubbles give that sort of dynamics. But I think for the transitions that are most visible with gravitational waves, you have bubbles that are very fast. And this is actually bad for baryogenesis. And I think that it's very hard to actually probe the region that is good for baryogenesis, where the phase transition is, where the bubbles are slow and have a terminal velocity that is much lower than the speed of light. So I'm not 100% sure that this is true for all models, but at least that's what I remember.
Prof, you had a question?
Yes.
Please.
So let's suppose that gravity waves of the type you described are observed at LISA. So what could we learn from them about the phase transition? And in particular, would we be able to tell if it's related to electroweak physics or not?
So of course, it's very hard. But first of all, just from the coincidence that it is exactly the frequency that you would expect from the electroweak phase transition. But then if you discover it, what would happen is that there will be a huge effort in trying to pin down the exact experimental predictions of the electroweak phase transition. Right now, it's still hard. I mean, there's people running these huge simulations of bubbles, and there's still arguments about what is the exact spectrum, especially in the UV part, which is very sensitive to the microphysics model. The IR part is given by just general GR thinking, but the UV part is super sensitive. And so just from the frequency spectrum, you could do it. But then if you are even looking maybe 30 years in the future, and you imagine you build an even better detector, and you look for the inhomogeneous signal, and you see 100% correspondence with the CMB, a full correlation with the CMB, that I think would be a very clear signal that this is something in the standard model heat bath at temperatures about 100 GeV. It's very hard to imagine it's something else. But of course, you should see something in colliders that tells you that the electroweak phase transition is actually first order and not a crossover. So
thanks again to Michael.